Hello everyone, we are going to present our Capstone 1 project, which is step-by-step calculation of the Penman-Montieth evapotranspiration FO56 method 1, and our group name is Magenta and our group member is I am Qazi Tariq Islam and following one Qayyum Hussain, Kevin Bhai Mistry and Rina Sreshta. So, what is evapotranspiration? The term evapotranspiration is commonly used to describe two processes of water loss from land surface to atmosphere, evaporation and transpiration. So, evaporation is the process where liquid water is converted to water vaporization and removed from the source such as the soil surface, wet vegetation, pavement, water bodies, etc. And transpiration consists of the vaporization of liquid water within a plant and subsequent loss of water as a vapor through leaf stoma. So evaporation and transpiration occur simultaneously, and both processes depend on solar radiation, air temperature, relative humidity, and wind speed, and some other factors. So transpiration rate is also influenced by crop characteristics and environmental aspect and cultivation practices. So evapotranspiration is defined as the rate at which rapidly available soil water is vaporized from a specified vegetated surface, which is defined by Jensen in 1990. And another scientist called Allen, he defined as evapotranspiration as uh, a ET rate from a uniform surface of dense, actively growing vegetation having specified height and surface resistance, not short of soil water, and representing an expanse of at 100 meter of the same or similar vegetations. The concept of ETO was introduced to study the evaporate demand of the atmosphere independent of crop type, crop development, and management practices. So, a large number of empirical methods have been developed over the last 50 years to estimate the evapotranspiration from different climate variables. Some of these derive from the non-well known Penman equation in 1948 to determine evapotranspiration from open water, bare soil and grass based on combination of energy balance and this type of formula is given here, and various derivation of the Penman equation include a bulk surface resistance term Montieth in 1965. The resulting equation is called Penman-Montieth equation, which is described here. And so an updated equation was recommended by Food and Agriculture Organization in 1998, which we call FAO56 Penman-Montieth equation. We are simplifying the second equation and utilizing some assumed constant parameter for a clipped grass reference crop, and we get these equations. In 1999, the Irrigation Association IA requested the Evapotranspiration in Irrigation and Hydrology Committee, Environmental and Water Resource Institute ASCEET to establish one standardized equation for estimating the parameter to gain consistency and wider acceptance of ET model, which is known as Howell EV 2006 model. The ACW EWRI standardized the reference ET equation based on the FAO56 Penman-Montieth equation for a hypothetical crop, which is given as this equation. So the objective of the publications is to provide the step-by-step calculation of the reference evapotranspiration FAO56 method for a given location from the available weather data. The FAO-Penman-Montieth method to estimate ETO can be derived where ETO, the reference evapotranspiration, which is millimeter per day, and Rn is net radiation of the crop surface, and there's others some variable we are using for the equation. So the reference evapotranspiration ETO provides a standard to which evapotranspiration at different period of the year or in the other region can be compared, and evapotranspiration of the other crop can be related. So we have to calculate every steps to determine the ET values. So the first one is mean daily temperature, and there is the equations. The second one is we have to find the solar radiations and convert it into uh, from watt meter per day to megajoule per meter per day. So our elevation is more than 2 meter above the sea level, so we consider uh, the two different cities wind speed we collect from the data collection center as nasapower.com. Okay, so our step 4 is the slope of saturation vapor pressure, and the step 5 is to determine the atmospheric pressure, where we can use the two different cities the z values. Okay, the step 6 is psychometric constant, where we gonna use the previous the value of p, and for the delta term we're gonna use the wind speed of the two different cities for the AV days. And the step 8 is the PSA term for auxiliary calculation for wind term. So and step 9 is temperature term, and we'll in this equation we're gonna use the value of u. And step 10, the mean saturation vapor pressure, and for this we have to find the ET max first, and then find the ET mean, and we will mean the two vapor pressure. Step 11 is to calculate the actual vapor pressure, which is EA, and we have collect the only one relative humidity data. That's why we take the RH mean data in this equation. And step 12, inverse relative distance Earth Sun and the solar declination. So these are the two data, and we are using the Julian day as J. So for the conversion of latitude in degrees to radian, first of all we get the latitude for Beaumont and Amarillo in distance2.com website, and put it here to convert into the radians. And step 14 is sunset hour angle, and we will gonna cos inverse and putting the radians value, and we'll find the set hour angle. And for step 15, extraterrestrial radian, which is RA. And for step 16, the clear sky solar radiations, RSO. And step 17 is the net solar or net shortwave radiation, RNS, which is deducting 1 minus A into RS. And step 18, which is net outgoing long wave solar radiation, which is RNL. And for the final step, first of all we have to calculate and determine the radiation term of ET, which is ET radiation. And then we have to determine the wind term, and for the final reference evapotranspiration value ETO, we have to add these two terms and get our ETO value. And we collect all the data, most of the data from the NASA Power dataxs.com, and for the latitude and the longitude we get the data from distance2.com.
First of all, we import some libraries like pandas SPD and operating system, and importing math for using math function from matplotlib, import pyplot as plt for uh, graph. After that we define some constant exponential 2.7183 base of natural logarithm, and z underscore b equal to 5 elevation above sea level meter for Beaumont, and z underscore a equal to 11 18 elevation above sea level meter for Amarillo, and GSC equal to 0.0820 solar constant megajoule per square meter per minute, and A equal to 0.23 Veldu or canopy reflection coefficient, and LB latitude of Beaumont and LA latitude of Amarillo. Sigma Stefan Boltzmann constant. We are defining path, set working directory, and read the data, and read the data from the CSV file. Change the directory and read data from CSV file.
So first of all, we define the function to calculate the evapotranspiration. There are our seven variables. T max, it's a maximum temperature in a degree Celsius. T minimum, minimum temperature in a degree Celsius. R is solar radiation. It's in a watt per meter square per day. And U2 means it's a wind speed at a 2 meter above the ground level, and it's in a meter per second. So RH is a relative humidity in a percentage, and J means the number of the day in a year. The L means it's a latitude in a decimal, it's in a decimal degree, and the Z means elevation above the ground level, sea level, it's in a meter. So our first equation is to calculate the mean temperature. That's when a T mean. So it's a T max plus T minimum divided by 2. So we have RS, to convert the solar radiation in watt from the watt to megajoules. We have to uh, uh, we have to do R into 0.0864. So now to calculate the slope of the saturation vapor pressure, we divide this equation in a two part, numerator and denominator. So it's convenient for to calculate, and then we calculate the atmospheric pressure. It's in kilopascals, and psychometric the psychometric constants also in a kilopascal per degree in a Celsius. After this is a delta term and a psi term, and it's a temperature term. So now the saturation vapor pressure at a maximum temperature we can find using this formula, and to calculate the saturation vapor pressure at a minimum temperature we can use this formula, E minimum. So it we can calculate the actual vapor pressure using the uh, saturation vapor pressure and at a maximum and a minimum. So now it's a inverse relative distance from the earth. So this is a solar declaration, and this is a conversion of the latitude in a degree to the radian. So we have to divide the we install the maths library for it, and we use this formula. After that we are breaking the equation for the external radiations. So we it's a temperature 1, temperature 2, and for the clear sky solar radiation we use this formula. Now we are breaking the equation in net outgoing long wave of the solar radiation. It's E2, E1, E2, E3, and the final one is the net going long wave solar radiation. So to find the net radiation, we just have to do Rn as minus Rn1, so we can get our net radiation. And radiation term, uh,
we use a DT in RNG, so wind term and a final reference evaporation. So we used a round ET into 4. So we didn't, for the written program we did this. So now we for the Julian, it's for the Julian, for the function we extract the function a for the every, from the first day to 165 day we extract a Julian. These are for the Bowman T max b, the, it's a denoted Bowman, and for the Amaryllis we use a Tmax A. To extract the temperature of the Bowman in a Tmax B minimum, extract the solar radiation in the Bowman, we did the whole thing. And for the Bowman then Amelia.
So now to calculate the evapotranspiration for each day for a given year, we are using for loop. Our for loop ranges from 0 to IDX. The value of IDX is length of j, which is 365. Inside for loop, we are calling the data from our CSV file, maximum temperature as T max B for Beaumont and minimum temperature as T min B, and so on. Now we are calling our defined function et so that we can calculate our evapotranspiration. And here in et not b dot append we are storing our each value from each iteration into et not b, um, and we are doing the same process for Amarillo. Then after that mm, we are saving our data into the Panda series data frame. And then after that we collect our data and save it in a CSV file, naming it final data. So now we have to plot the graph of evapotranspiration versus day for both the cities. We create a 2 by 1 plot, that's your same axis. We define fig comma axis, where fig is for overall figure and axis is for axis. Here plt dot subplots means that we are dividing our plot into two subplots. Share x equals to true means that they share the x-axis. Ax0 is for plot 1 and dot grid denotes that we are adding grid to our plots. By using dot plot, now we are plotting our graph. D is x-axis and et not b is evapotranspiration of Beaumont, which is for y-axis. The color is selected as R and marker is circle. We have not defined line style, and it is same for axis 1. We have set our title as for Beaumont for Beaumont City, and for Amarillo for um, Amarillo City. Then using plt.x label, we give label to our plot, which is days in the x-axis, and in the y-axis evapotranspiration, whose unit is mm per day. Now using dot legend, we give our legend in the upper right corner for both the plots. Plt.show is used to show our plots in the console. So this is our graph for evapotranspiration versus day. Here we can see that for Beaumont, from around May to September, our evapotranspiration is higher, and from September to February it is lower, ranging around 1 per day. And for Amarillo we can see that it is quite dispersed and its average is around 3 per day. So our next task is to create a user interface for the calculation of evapotranspiration. For that we imported PySimple GUI as SG. Here as dot theme and gives a color to our interface. After that we define our contents for the window. Inside the layout we give our input, we describe how our input how we want our windows to be like. Here we have given 8 inputs, because we have 8 variables in our um, function. Inside the as the text, we write the text we want to display in our interface. Inside the as dot in the as what sg dot input does is that it reads the text as an input, and we have given a key as input 1 for first text and input 2 for second text, and so on. We have also given a button, where button as calculate, so that when we click that, we can calculate our evapotranspiration. And when we click on s.g exit, we exit from our interface. So now we create the window with title and layout. Our title is estimate evapotranspiration, and we are calling our layout which we defined earlier. Now we have to create an event loop. So inside our loop, we have included a if statement, so that when our event is calculate, it will go inside that if statement, and it will ask us to input our 8 variables. And when we after that, we have called our et function, which we have defined earlier, which requires 8 inputs. So after that, we want our output to be the evapotranspiration is, and our value is et naught, which we will get from the function, and its unit is mm per day. So after that, this is there is another if statement, so that when the user wants to close the window, the user can click the close button, or if the user clicks the exit button, with the interface will close. And we can see the our interface in the next slide. So you can see our user interface here. The first picture is before we input our data, and in the second picture you can see that we have input our data, and after inputting our data, we click calculate, and it gave our evapotranspiration as 1.0106 mm per day. So using this interface, we can calculate evapotranspiration for any location, if we have these 8 variables are known.
Our main goal is to calculate the reference evapotranspiration estimation method is based on climate data which can be obtained from a local weather station, or you can input your local weather data like maximum temperature, minimum temperature, solar radiation. So that kind of user interface, makes the life easier for calculating the evapotranspiration, because anyone who do not have any coding experience or coding knowledge, they can easily use it and calculate the evapotranspiration for any type of crops, and make it life easier. And you can get the link of the user interface in our video descriptions.